SEC basketball Hello, everybody.
Hello.
Thank you. So we have a homework due on Wednesday. And I get confused. This was due 29th, correct? Did I say 29th?
That is what you said, yeah.
Yeah. Okay. I have it wrong in my. Okay. Let's midterm 3 now, not 2. I also wanted to say that there was at least one or two requests for if there is any help desk available for physics. There is a physics department help desk. This is free. These are usually managed by graduate students in physics. Almost every day, about 3 or 4 hours of help hours is available. The information is, I have posted this on our course website. So right on top, there are some resource materials. So look up on course website. It's also available if you search for physics help desk and SIUC on Google, you should be able to reach that directly, but there is a link for that on the course website. That's just for your information. There's also the quiz that I should go over before I begin. The quiz said it's about kinetic energy. Kinetic energy is half mv squared, right? And it asked, can this be negative? Notice that velocity square will always be positive, right? Even if it is negative, velocity square will always be greater than or equal to 0. Mass, the way we understand it as of now, is greater than or equal to 0. So kinetic energy in this construction is always greater than or equal to 0. But the question is for you to ponder as to is it possible to have it negative or not? But in this simple construction, the answer is no, it cannot be negative. But also remember that in the context of cosmology, we have what is called dark energy, and in very naive, simple terms, it is possible to explain this using the idea of negative mass and so on. So it's a good thing to keep in mind when you're exploring bigger concepts or new concepts if you want. But the answer is no, it cannot be negative. Negative, it is always greater than or equal to 0 in our construction as of now. Okay. We are talking, we were talking about work, kinetic energy, and potential energy. That's the 3 concepts we have introduced. And the idea is to write or work out things in terms of energy conservation instead of talking about, using the force equation. So let me introduce the idea of work done by a force. We also talked about kinetic energy.
जारी एक काम को मैं डार्लिंग तुम सवार करूँ ओके 90% लिया जो
muted, I guess. Okay, helps to mute everyone. So if you want, you just unmute yourself. Okay, kinetic work, kinetic energy, and that's a potential. That's the 3 concepts we have introduced as of now. And let me summarize this very quickly. We have Newton's law, which tells us that given a mass m, which we often say is our system, the motion of the mass m, which is the acceleration of the mass m. So the product of mass times acceleration is equal to the sum of the vector sum of the forces acting on this. So typically we say this is F1 plus F2 plus so on. So let's say, let me specialize here. Typically we have gravity acting on this. So usually we are on the surface of Earth, and there is a gravitational force acting on it. And let me isolate that force specifically. And other forces, I call that F1 plus F2 plus so on. It's just that I'm last time I pointed out that gravitational force is independent, or the work done by the gravitational force is independent of the path along which you go. So we want to give it some special status there. So that's why I wrote it specifically as mg. If we integrate this with respect to the distance along which it is going. So you start from the Newton's law, multiply it with dx. If it is just constant forces coming into picture, you can just multiply it with the displacement, and that's good enough. If it is not, you break it into small displacements, and then you integrate it. And you integrate it along a path. Path, of course, has an initial point and a final point, which is given by the specific nature of that. And we showed that this is nothing but a change in kinetic energy. So the left-hand side, which is the mass times acceleration, which talks about the motion. And here also we have information about the motion. Kinetic energy means by construction or by definition, it has to do with motion, but more importantly, it depends only on the final and initial points of the path. Like even though you could have gone using any complicated path, it only depends on the initial and final points in the path. So that's an important point here. And then we said this is the work done by gravity. plus the work done by the first force. So this is a general scenario. If there are many forces acting, work done by all the forces together. And we said this involves the definition. K is kinetic energy, that is half mv squared. So change in kinetic energy would mean the change in kinetic energy is half mv final squared minus half mv initial squared. Again, I keep stressing the point that the change in kinetic energy depends only on the final and initial point. That's an important fact there. Now, the work done by gravity, similarly, it turns out to be, it does not depend on the path, and it only depends on the final and initial points, and it can be written as change. Whenever it depends only on the final and initial point, it is not necessary to write it as an integral. It is only the final minus initial, right? So it can be written as a difference in two quantities, and that's equal to, so here U is equal to mgh. So that's something we learned last time, or we observed last time. The work done by gravity is independent of the details of the path. It only depends on the final minus initial quantities, and in that case, U is called the gravitational potential energy. So this is called a gravitational potential energy. I can write it in there. So delta U would be equal to, so delta U again, mass and gravity does not, oops, I should move the camera, I suppose. Mass and gravity does not change, so it is mg at final, whatever is the height at the final point, minus mg at initial. So some definitions here. V is velocity, that's standard. H is the vertical height. A vertical height from the ground. Notice the negative sign that I've introduced here, that's purposeful. That allows me to take it to the left-hand side. The work done by gravity is a negative difference in potential energy. So take it to the left-hand side. So change in kinetic energy plus change in potential energy is equal to the work done by all other forces. And why did we move this to the left-hand side? Because anything on the left-hand side depends only on the initial and final point. Very powerful statement there. No need to worry about what kind of path we took, and we will do a few examples. And that will be our state. This is usually called conservation of mechanical energy. Or let me just say mechanics work energy. Yeah, let's just say this is work energy theorem. Let me keep that general instead of going to the specific nature of what that statement is. Now, how do we use this? Let me go to a quick example of how this shows up. Let's go back to an example where we started sometime back. There we use the idea of work, but now we will use the idea of potential energy to do the same problem. So example, let's have a frictionless incline and a mass M sliding on it. So that's frictionless. So we know that in that case, we have only two forces acting. So it's angle theta. We know that mass times acceleration for this problem. Just to recognize the forces that acting on it, that's mg. Mg acting downward, and that is normal force acting perpendicular to the surface. Immediately, we recognize that our energy, work energy theorem will state this will correspond to the change in kinetic energy, plus this will correspond to the change in potential energy, which I move it to the left and say this is change in potential energy, and that's equal to the work done by the normal force. But in this case, the mass is sliding along the incline. The normal force is always perpendicular to the displacement, so the work done by the normal force is 0. So what we have is the change in kinetic energy plus the change in potential energy is equal to 0. So let me write that down explicitly. So that's K final minus K initial plus the potential energy change. So that's U final minus U initial is equal to 0 because the normal force does not do any work. This can be stated as,
What happened to the gravitational work?
that's the delta U. Remember, mg became the gravitational potential energy. Right?
Oh, okay.
U is mgh here. So so this is U is mgh. Right? So that's exactly the work done by gravity. Now we are talking in terms of potential energy. So no need to talk in terms of work, instead talk in terms of potential energy. The crucial point here is that not all forces have a potential energy associated with it. There are only two forces we'll come across in the whole semester here, which will have a potential energy associated with it. One will be gravity, and the second will be the force due to a spring that we will introduce today. So these two forces are special. They will be called conservative forces. Okay, so that allows us to write this equation as K initial. I can either write final is equal to initial or initial equal to final. So that's K final plus U final is equal to K initial plus potential energy. So notice what we are saying, kinetic energy plus potential energy at the final point is the same as the kinetic energy plus potential energy at the initial point. In fact, you say that this remains constant. You can take any point and this remains constant. And that's called the conservation of mechanical energy. So this is called conservation of mechanical energy. And it's very clear, and only under special situations where the work done by the forces is equal to 0 does that happen. But if that is the case, then we can do simple things like we have, let's say this is your initial point, that's your final point, right? So we can immediately say this is half m v final square. That's your kinetic energy at the final point, plus what is the potential energy at final point? It is simply given by mg h final. What is h final? Here, let me erase these things. So that's your h initial. I can take any reference here. That's your h initial, and that's your h final. it doesn't matter what reference you choose. Typically, of course, you would choose this to be 0 so that one of them goes away to 0. So the energy, total energy is the kinetic energy plus the potential energy is equal to the kinetic energy plus potential energy earlier. So very simple, and if it starts from rest, so if it starts from rest at this point, if it were at rest, then this goes to 0. If it starts from rest, so this is starts from rest. That's based on the initial condition. And let's say H final is equal to 0. So this is equal to 0. Why? Because I choose my origin. I choose origin. So origin is equal to 0. So I have a choice of the vertical origin. If I choose that to be 0, so this goes to 0, that goes to 0. So I immediately have a simple equation. Mg H initial. I wrote some 6 steps here, but often based with a little experience, you would immediately say that, oh, in the initial part, all the energy is in the form of potential energy. As it falls, you're losing potential energy. So if the energy is conserved, it has to show up as kinetic energy. So at the final point, it has to show up as kinetic energy. In this simple scenario, the mass m cancels out, and we have V final is equal to 2g times h initial. So if the height was given to us to be height of the incline, notice typically we also often say that this is the length along the incline, but this is the vertical height. So if vertical height h initial was 5 meters, then that's equal to 2 times 9.8 times 5.0. So that's square root of 98, and that will be approximately 10. So that's 9.9 meters per second. In this form, we can also do, where do I go? Let's do another example of projectile motion. So let's say this is projectile motion. We did this long ago in lot detail. So you would say you throw a ball up in the air, and let's say that's your ground, and it is shot up or launched with an initial velocity v initial. And we could ask what is the energy or how high does it go, right? Let's say it is launched with an initial velocity v initial at an angle of theta initial. So let's say this is about 10 meters per second. And this could be 40 degrees. We can ask how high does it go? So that's how high does it go? But we do know that at this point, it will have some velocity. Right? It's not going to be at rest there. It will have the horizontal velocity intact there. It's only the vertical velocity that goes to 0. Its velocity here would be, let's call it V final. That will be equal to 10 cosine 30. Right? 10 cosine 40. That's because its horizontal component stays the same. Right? That's not going to change. It's not accelerating. And let's ask what is the height h. Earlier we would have worked it out using kinematic equations, but now we simply say kinetic energy plus potential energy. So that's your initial point, and that's your final point. So half mv initial square. So the total velocity, notice this is not a component of its velocity, the total velocity square plus mgh initial is equal to half mv final square plus mgh final. Right, that's your h final. H initial is equal to 0. I can choose this to be 0. I choose my origin. So this is because I choose my origin to be right on the ground. Then I have height is equal to 0. There is mass in each term, so that cancels out. And what I have is V initial square, or half, let me write this as V initial square is equal to V final square and plus 2GH final. And that should ring a bell. That is exactly one of the kinematic equations that you came across. But this time, this comes out immediately from the conservation of energy principle. So we know the numbers. V initial is 10 square. That's equal to V final is 10 times cosine of 40 square. And I'm interested in calculating what is the height. So that's plus 2 times 9.8 times h final. So that allows us to calculate h final. So that's 100 minus, I'll help here. So 100 times, no. Square it minus 100 and then divided by 19.6. That leads to a height of 2.1 meters. Okay. Simple example where this shows up. Let's go back to the incline problem and let me elaborate on something interesting there where the path independence of this whole problem shows up very nicely. So we had an incline, that's your mass m that is going around or going on that surface. We said it's a frictionless surface. That's your final point, and that's your initial point. And we said that if I want to calculate the final velocity, it is half mv final square plus mg h final is equal to half mv initial square plus mg h initial. Again, remember what is going on. There was one more force, like that is the, of course, mass times acceleration contributes to this, gravitational force contributes to this, and there is a normal force, but it doesn't do any work. So we say that's equal to 0. And we are assuming that this is frictionless. And we also know that this is path independent. So can we do something else? So let's say instead of a straight line, this is actually going along a curved path. Think of a slide in a park. And let's again say this is final point, and that's your initial point. And the mass at every point is just sliding tangential to the curve that I have described. The normal force again will be perpendicular to that. And the work done by the normal force will again be 0. So what are the forces acting on this? Again, it is mass times acceleration is equal to mg plus the normal force. Right? There is no other force acting. We say there is no friction acting on this. In that case, that's the only forces acting on it. And the work done by the normal force is indeed equal to 0. Again, because it's always perpendicular to the velocity vector, or if it is perpendicular velocity vector, it's perpendicular to the displacement at every instant. And immediately you would say change in kinetic energy plus change in potential energy is equal to 0. And again, you get this equation. Same equation again is applicable, but this time it is applicable for a curved surface. For that matter, it doesn't even have to be a simple curve like this. A complicated structure like this, a roller coaster, for example, you could start from point A and you could reach point B. It doesn't matter how deep you went, how high you went. Overall, it is only the change in the heights that matter. So if you know the velocity at point A, if you know the velocity at point B, you can calculate everything else. So let me say this is height HA and that's height HB. So again, I would say half mVA square plus mg height at point A is equal to any other point, and I pick it to be point B here. So half mv B square plus mg height at point B. Again, assuming that there is not much energy lost in friction. If this was frictional surface, then we do have some energy lost into friction, and that would mean that the velocity will be smaller at point B. So that leads to very easy analysis of complicated problems like this roller coaster example, where the surface could have been having a very complicated geometry. It leads to very simple analysis in there. And there are homework problems related to that. This shows up in your homework. So I've shown that gravitational force is, the work done by the gravitational force is independent of the path along which you go. And these forces typically are called conservative forces, as I will highlight again on Monday or Wednesday. But at this point, I want to introduce one more force, and that is the force due to a spring. So this is not belonging to the 4 forces we talked about earlier. So this is going to be a new force. And the nice part is that it is also a conservative force, and you will be able to associate a potential energy associated with it. So this is a force due to a spring. And it's often called the Hooke's law. Let us consider a horizontal surface. So this is let's say this is ground. And let's say it is frictionless. That's just to take away one of the forces we usually have. And let's say this is a wall. That's a wall, that's your ground. Let's attach a spring. A spring is typically represented as a coil. Right? That's a coil which can actually stretch or get compressed. And let's say that's connected to a mass M. In equilibrium, it just stays, it is neither stretched nor compressed, so it just stays here. So let's have that special position, and let's call that 0. So that's x equal to 0. So I choose my origin or the horizontal origin for the horizontal axis to be at the point where the mass is at rest, when the spring is neither stretched nor compressed. But now let's stretch this spring to the right side. Let's say this is mass is somewhere here. Now I've stretched this, I pull this out. That was your x equal to 0. And let's say that's your new x, right? So that distance is x. This has been stretched, so I show that as, so that's a stretch. But the important point is this stretch will be characterized by this x, the variable x. That's what we mean by a stretch. But we can also compress it. It doesn't have to be stretched to the right side. This is reasonably solid in form, and I can even compress the spring. So the opposite stretch would be, so that's your x equal to 0. And this time it is to the left. I'll still call it x, but understanding is that x is a negative number then, right? Like we talk about a negative number line. X could be negative, so it is on the left hand side. So the sign is there inside the variable x. So that's your mass m. And this time it is compressed, so I'll show that as, so that's the compression. And clearly, one can think that, okay, what will be the, or what we want to know is that what is the force that acts on this mass m when it is stretched versus when it is compressed. In either of those scenarios, we want to ask what is the force that acts on it. And our model will be that when it is pulled to the right, it is going to, the spring is going to pull it to the left. That's going to be the force of due to the spring. And in this case, when you compress it, it's saying, no, I don't want to get compressed. It's going to go the other way. So the force is to the right. So that's your force due to the spring with the direction. That's the force due to the spring with the direction. Notice when the stretch is to the right, the force is to the left. When the, if I call it still the stretch, when stretch is to the left, the force is to the right. By stretch to the left, I mean a compression. So the force due to the spring is always opposite to the direction in which you pull it. So that seems to suggest we can have the following model. So that's what Hooke's law is about. So Hooke's law says that in the description I made on the left, the force due to a spring is equal to, let's say, everything happens in the straight line. So let me include all the sign. It can only be positive or negative. All the signatures are there in the variable itself. So the force, which can be positive or negative, is equal to negative k times x, where x is whether you are pushing it to the right or left, it is a stretch. The compression also, compression means it's a negative x. And k here is called the spring constant. And what does that mean? Of course, the force depends on how much stretch you make, but it also depends on what kind of material you have constructed the spring out of. If the material is very stiff, then the force will be very large. If the material is not very stiff, for example, a rubber band, it will have a lesser amount of force. It will require a lot more stretch to do the same job. So that leads to the idea of what K could be. A couple of examples just to give you the extreme values. So K is of course the force due to the spring over the stretch. Right? Let's take two extreme examples or two values of two examples in which these come out to be, one is very large and one is very small. Where do you see a spring? One of the places where you see a spring is inside a car. So when a car is going on a bump or a speed barrier, often it gives, if not for the shock absorbers next to the tires, you might experience a very rough ride if you want. So this will be called a car shock absorber. That's one example. That's a very stiff spring. And more importantly, what is the force that is causing it to stretch? That is usually the weight of the car itself. Weight of the car is about 2,000 kgs, and the amount of stretch might be about 5 or 10 centimeters. So if you were to divide mg over x, this can amount to a k of about 10 raised to 5 or 10 raised to 6. Let me put it on the extreme side. Let's say a very heavy car or a truck. So this is 10 raised to 6 Newton per meter. That's the scale in which you can have. Another spring could be a simple rubber band, right? Or sometimes if you have opened a ballpoint pen, there is a small spring inside that. That is what actually makes it, when you click on it, it opens and closes. So that's a spring inside a pen or a rubber band. K could be significantly small. We might just have 1 gram, let us say. So that's that gives you about let's say 100. So this could be somewhere 10 raised to 2. Still, it's a big number in the sense it's 10 raised to 2. But this is the range in which you can think of in the two examples that I gave. Of course, you can think of much smaller in very specific examples, but most of the examples we will deal with will involve a car or a rubber band and so on. A 20 kg mass stretching a spring by 20 centimeters. Those are the examples we will deal with. So let's do a very simple example just to clarify this. Let's say a spring is sitting on a ground. So that's the ground. And this is a small, tiny platform there. And there is a spring that's holding on that platform. I can have a mass M sitting on it. And now let's again analyze what are the forces acting on that mass M. Just to show how you go about identifying what are the forces acting on it. Remember that rough list that we had gravity as one of the forces, then we had normal force, and then we had force of tension if it is connected to a rope, or if someone is pushing or pulling, or if there is a contact force. Then we had friction, and now we want to add a force to this list, and that is the force due to a spring. And again, for this particular mass, let's analyze what are the forces acting on it. It is on the surface of Earth, so that is mg acting downward. And next now comes the normal force. This is a confusion now. Is there a normal force acting on it? Yes, there is normal force acting on it in the sense that, yes, this is on the surface, sitting or in touch with the surface. But notice that this is actually, the ground is the surface, and it is a spring. This platform is just a design to connect it with the spring. So when it is the spring it is directly connected to, either you accommodate for it using the normal force or you accommodate it for the spring. since in this context we are talking about, we are interested in how much this spring compresses or not, then we talk about the spring and not the normal force. So we shouldn't be introducing both. If we introduce a normal force, we don't talk about the spring. Effectively, what we're saying is that this tiny platform that's there is massless. Like we are not interested in the motion due to that, and that is not exerting any normal force there. So the force that is exerted on the mass m is due to the spring. So I would say this is kx, or the force due to the spring. It's not the normal force, it is the force due to the spring. So another way of saying is that we have a more detail for the normal force that's acting on it. This could be a weighing scale. A weighing scale actually has a string inside it, and it is how much you stretch or compress on it that actually decides what's the what it weighs. There is no friction unless we try to move it around in the horizontal direction. It is just static, so there is no friction. It is not connected to a rope or anything, so there is no force of tension. So that's your two forces that's acting on it. And if it is not moving, you would say mass times acceleration is equal to mg plus the force due to the spring. If acceleration is equal to 0, you have minus mg plus, if the stretch is positive, so x is positive here. So so fs, if x is positive, then this will be minus kx. So minus kx. So mg is equal to, kx will be in the downward help here. Now, if it is compressed, it is in the upward direction. That's correct. So that's equal to minus kx. Here, x is understood to be negative. So that's what it means. So k is equal to mg over x, and you can calculate the stretch that comes in the spring. So that's a very simple example where you see the spring coming in.
Why is it that the spring force is negative?
It depends on the choice of your x. It's sort of discomforting here. So let's say that's your 0. Right? Now, typically you would say this is compressed, right? So you would compress this. Now, if that is 0, and if I say that's positive, it depends on your choice, then this is going to be compressed, right? So that's your x. From the equilibrium, it is pushed down. If you want to measure it like that. If I were to choose this to be positive in this direction, then that is a more standard way of looking at it. So then you don't get this minus sign. So let me say, if this was the case, then you would say this is mg is equal to k times x. If I choose this to be the positive. If I were to say positive is upward, then x is actually negative. So here, x is actually negative here. So effectively, you get the same thing. Is that clear? Did I clarify?
Yeah.
Yeah. So yeah, commonly this is what you would do, but then I started by saying, oh, that's the positive direction. So that's effectively correct. Okay. In the last few minutes, as I said, I propose that I will introduce the new Hooke's law, or the force due to the spring, and I also suggested that this is a force that does not depend on, or the work done does not depend on the path. So let's calculate the work done by this force, and let's stop after. And we'll come back and do the rest. So let's say work done by the force of a spring. So that will be equal to work done by the force due to the spring will be, you go from initial to points final. So let's say x initial, x final, and the force due to a spring is minus kx. So let me say this is Fs dotted with dx. Let's say. Everything in a spring happens in the same direction, so I don't need this vector sign. So this is x initial to x final, but the force is minus kx, so that's minus kx times dx. Right, everything is taken care of in the sign. The minus sign is because of the Hooke's law, or if you want to look at it as a dot product, you can see it from the cosine of 180 degrees that's coming in there too. That's equal to minus k integral of x dx, which is a very simple integral. That's half x squared. And that's equal to minus k half x squared evaluated from initial to final. That's equal to, let's write this as minus of half k x final square minus of half k x initial square. If I were to identify this as a change in negative potential energy, I would say the potential energy in a spring is half k x squared. So the energy stored in a spring, if you want, is related to the square of x, whether it is compressed or stretched, it doesn't matter. It's the same amount of energy that will be stored. We'll come back and talk about this more next time. For now, I'll stop here. Thank you.
Okay, so I just want to check up on this spring thing. So when the direction that the change in x happens is negative, the spring force is also negative.
Tell that again.
So when the change in direction of x is negative, in the case of which direction the spring is being sent, the spring force is also negative?
Oh, no, that's not, okay, so let's put it this way. Let us say this is a, here. So this is a spring, right? Let's say I go from x initial to x final. So that's your x final. So I'm stretching it to the right. So x is assumed to be positive in here. So my delta x, if you want, dx at this tiny point will be dx, correct? If you want to see
the camera needs to be moved.
Yes. So that's your dx, right? If you want, so there are two ways of looking at it, either in terms of vectors or in terms of simple variables. So if I see it as a vector, so this is my force F. So, but the negative sign is inside the sign itself. So if I were to do force dotted with dx, right? So now I first need to know what is my force. If I were, notice the negative sign is inbuilt inside this force. So even though I show this as a negative sign, when I'm doing the dot product, I have to keep it in the front direction, but I know that the force is in the negative direction. So explicitly look at it. So that's your force, and with the kx in it. So that's your dx, right? If you move this way, so that's your dx, but the force is this way, so that's minus kx. Right? Notice if x is positive, that's in the opposite direction. If it's in the opposite direction, this will change direction. So either you say this is a vector nature that is giving you, or you say it is minus kx times dx. So, so my F dotted with dx is equal to, either way, this is minus kx times dx. And I think that's your question, right? Is that?
Sort of. Okay, could we apply this to the box thing again? So like, in the case where there's the box resting on the spring on the ground, if we determined the spring being pushed downwards as the negative direction, that would mean that the final equation would be mg equals positive kx?
Not mg, so let's see. I think
What? But that's what you said the equation was.
Not mg, right? Kx, you mean?
What, mg equaling positive kx?
Yeah. In this particular case, it will be yes. So let's see. So your point is that this is mg, right? But we want to do the work done by the force due to the the spring, right? That's your Fs, right? So now let us say first we need to decide where we are going. So if I'm going from the top to the bottom, right? So I'm going to the top to the bottom. So that's my initial point, and that's my final point. It is like saying that I keep my mass and I compress it. Correct? So that's one possibility I can choose. So that's your x initial to x final. That's my delta x. So dx is downwards. What's the direction of the force due to the spring? That's upward. Right? When the dx is trying to go to downward, then my force is upward. So I have to decide again my kx. So let me say, I think there we chose our positive to be downward, right? So that will be negative kx then again.
Okay, so the reason why kx was negative is because you chose positive to be downwards.
That's correct.
Okay, so if we chose positive to be upwards, then kx will be positive.
Exactly.
Okay, thank you.
And one has to be careful, I completely agree, but with that notation, it should always work. Okay. You want me to complete this?
I understand now.
Okay, so check it out and hopefully that works out. Yeah.
Thank you.
Okay, good.
Have a good day.
You too. Bye-bye.
Goodbye.
Questions? Thank you.